Alright, so today we're going to be talking about how to solve horizontal launch problems for projectile motion. Alright, so before continuing, you want to have out your notes for the post-lab discussion for projectile motion where we did the video analysis, or you can watch the post-lab discussion screencast that I have on YouTube. But here are the equations that I would use in regular, where we have a different set of equations for the horizontal direction and the vertical direction. Now in honors, I do a slightly different equations, but they essentially mean the same thing. The only difference here is that in honors, I separate the initial position and the final position, whereas in regular, I combine them into delta x. Likewise, you'll see the same thing. For example, here, for the regular version of this equation, you would just see a delta y here. Likewise, here, I would combine the y final and the y initial into a delta y. Otherwise, they're essentially the same equations. Okay, so before we do our example problem, a few things that we need to remember from our post-lab discussion for horizontal launch problems is, the first thing is that we've got the acceleration in the x direction is 0 meters per second squared. The acceleration in the y direction is negative 9.8 meters per second squared. And we also have, for horizontal launch problems, that the time variable is the only variable that the x and y directions can have in common. So the x and y directions can share the time variable. Otherwise, all motion is independent in the x direction and in the y direction. So those two things don't have anything to do with each other as far as problem solving goes. And most importantly, we want to make sure that when we list our variables down, that we are very organized when doing so. Okay, so in this problem, we have a ball that's kicked horizontally off a 20-meter high cliff into the sea. If its initial velocity is 6 meters per second, determine how far it travels. So first up, let's list everything that we know. Now here, this is the table that I'll usually use for organizing my data. Now, if you are in my regular section, you'll see that this won't be here. And if you're in my honors section, you'll see that this won't be here. But essentially, we're doing the same problem. So I'll kind of do it at the same time. So first, we're going to list what we know for sure. Okay. Now, we're allowed to use our initial position, whatever we like. We want to make sure that we have a 0 meter here. So we have that. And we know that we want to find out how far it travels. So that's what the problem wants. And likewise, that's what we're solving for if you're in my regular section. Now, the problem also tells us that we have an initial horizontal velocity of 6 meters per second. So I'll list that there. And we know that the final horizontal velocity is going to be 6 meters per second as well. And that all has to do with the fact that there is no acceleration in the horizontal direction. Now let's move over to the y direction and see what we can figure out. We know that the cliff is 20 meters high, so our vertical displacement is going to be negative 20 meters because it's going to fall that distance. Now, if you're in honors, what you can do is just say, all right, the cliff is 20 meters high, so it starts off at a height of 20 meters, and then we have a final height of 0 because it falls into the sea. And you'll notice that y final minus y initial will give you that negative 20 that I'm using, that I wrote down there before. Now, moving to the velocities, we know that if you throw something or something's launched horizontally, as far as the vertical direction goes, it's like dropping an object. So it's y velocity initially is going to be 0 meters per second. The y velocity final is something that we do not know. It's not provided to us, so I'm going to write down missing here. And my acceleration in the y direction is negative 9.8 meters per second squared. So if we try to solve this problem right off the bat with our x equation, what happens is we will run into a brick wall because we do not have the time. So without the time, we have one equation and two variables, which is something we can't solve. What that typically means for projectile motion is we will have to work in the y direction to determine the time. So working in the y direction, we kind of have another question mark here, because now we're going to put on hold finding our delta x. We're going to put on hold finding our horizontal position, because right now the problem is we need to find time first. So working with our y, we see that the final velocity in the y direction is missing. So like in unit 3, constant acceleration unit, we're going to use the equation that is missing our final y velocity. And it turns out that it's this equation here. And we can go ahead and plug things in. We have negative 20 meters is equal to 1/2 negative 9.8 meters per second squared times time squared plus our initial y velocity, which is 0, times time. So the last term will cancel because of that 0. And now we have negative 20 meters is equal to, and now I'm just going to multiply this through. This is negative 4.9 meters per second squared times time squared. I'm going to fast forward a little bit, and it turns out that this time is equal to 2.02 or negative 2.02, right? From math class, whenever you take a square root of time, you do get the plus and the minus, and in physics, we're going to throw out this negative time because there is no negative time for now. So here, we have a time that we can use, and like we said before, that time can be used for both columns here. All right, so here we go. Solving for my delta x now, we have 6 meters per second times the time we just found. And that gives us 12.12 meters for the displacement. Horizontal launch problems, usually hard to come up with interesting ones. So if you can do this one, it doesn't get any harder or easier than this one. So you can practice this one a few times, check out the homework, and then we'll talk later.